Good day, mathophiles. Welcome to a discussion of concavity, which is a feature of the graphs of functions. We'll start by taking an intuitive look at a graph and making a very basic notion of what it might mean for a function to be concave up and concave down. We'll develop from that one of the possible definitions that can be given of concavity. Then we'll have a theorem that links that to the second derivative, and we'll work a couple of examples. So you see in front of you the graph of the function f of x equals x cubed minus 3x. This is sort of a standard issue cubic. And we want to take a look at this feature of various intervals on the graph, whether they're opening downward, as a downward facing parabola might, or whether they're opening upward, as an upward facing parabola might. And so we're going to want to call these sorts of areas where things are kind of facing down intervals where the function is concave downward, and these sorts of intervals over here to the right, we will call intervals where the function is concave upward. Pretty simple, intuitive concept. But now, let's take a look at a tangent to this curve, and let's begin on the interval to the left of 0, where this function clearly, visually, intuitively is concave down. And let's look at what the slopes of the tangent lines are doing. So if I start over here with x somewhere to the left of -2, and I allow x to slowly grow, what I see is that the slopes of the tangent lines, in other words, the values of the first derivative, are decreasing. It's upward sloping tangent lines becoming less steep. At some point, we reach this maximum over here. The first derivative is 0. And the first derivative continues to decrease. It's negative and its magnitude is growing. But of course, if you have a negative number with a growing magnitude, it's actually moving to the left in a sense on the number lines, becoming lesser and lesser. So it seems reasonable, based on what we're seeing here, to imagine that we could define downward concavity of a graph in terms of a decreasing first derivative. When we get over here to the interval where this graph is concave up, intuitively, we find that the derivative is increasing. Slopes of the tangent lines are growing. And bear in mind, again, when they're negative, a lesser magnitude corresponds to a greater number. So as these are getting shallower and shallower, the first derivative is increasing. And of course, it's even more easy to see once we get past that minimum that the first derivative is increasing. So we're going to use the increasing or decreasing character of the first derivative as a way of defining concave up and concave down. This is not the only way it can be done. It's the way the textbook does it that I use with my students, and I think it's a very good approach to take to the notion of concavity. So we're going to use this graphical exploration as the basis for a formal definition, and our definition will be, if f is differentiable on an open interval I, then f is concave up on I if f prime is increasing on I, and concave down if f prime is decreasing. Well, if you know a little bit about calculus, you know that for f prime to be increasing, that is in essence to say, if it exists, that f double prime is positive. And for f prime to be decreasing, providing that f double prime exists, it would then need to be negative. So you'll see now a theorem that encapsulates that. If f is twice differentiable on some open interval I, and if f prime of x is positive for all x in I, then f is concave up on I. And if f double prime is negative for all x in I, then f is concave down on I. So we basically have one of two ways of distinguishing concave up from concave down, and they're both equivalent. Is the first derivative increasing or decreasing? Is the second derivative positive or negative? And finally, just a piece of terminology. If f is continuous on an open interval containing some value x naught, and if f changes the direction of its concavity at that value, then that point is said to be an inflection point of f, the point x naught, f of x naught. Here is our first example, and it's a very traditional one. We're asked to analyze the concavity and locate the inflection points of a function g of x equals x squared e to the opposite of x. We're going to need the first and the second derivatives, and I'm going to assume that you have the skills to generate those. So I'm just going to give the final results factored, and you can stop the video and fill in the work if you'd care to. But G prime, this is just a product with a small bit of chain rule there with the -1. So G prime is x e to the op x times 2 minus x. And G double prime is e to the op x times this quadratic, x squared minus 4x plus 2. Now, second derivative is continuous, so it's only going to change signs at locations where it's 0. E to the op x is never going to be 0, so we just need to go looking for the zeros of this quadratic, x squared minus 4x plus 2. I will tell you that when G double prime is equal to 0, x is going to be 2 plus or minus the square root of 2. And if I approximate those to the usual AP 3 decimal places, I find that they are 0.586 and 3.414. If we then want to know the signs of G double prime on the 3 intervals that are defined by those 2 zeros, a bunch of ways we can do it. We can test individual points. I think the cheapest thing we can do is to just recognize that e to the op x is always positive. This quadratic opens up, which means it has to be of this character. It's got to be lower in the middle, so to speak, than it is off to the sides. And now we have everything we need to know in order to fully analyze the concavity of G. To the left of 0.586, G double prime is positive, which means G prime is increasing, which means G is concave up. Similarly, to the right of 3.414, between these two values, 0.586 and 3.414, G double prime is negative, which means G is concave down, and these changes of concavity at these 2 zeros are then inflection points. Not necessarily the case that a 0 of G double prime corresponds to an inflection point. There's got to be a sign change as well as a 0. Here is an example of a type that the AP Calculus Exam Development Committee people really like. They give you a graph of a derivative of a function, and they potentially can ask all kinds of questions. But what's of interest to us today is where are the inflection points, where are the intervals where the function is concave up or concave down. We're going to harken back to the definition that we gave at first, which is that a function is concave down if its first derivative is decreasing, concave up if its first derivative is increasing. So we're looking here at the first derivative of f. So what is f doing? Well, from -5 to -3, and we gave our definition in terms of open intervals. On -5 to -3 open, f prime is decreasing, so f is concave down. From there to x equals 0, f prime is increasing, f is concave up. And then we decrease again for a little bit, we increase again for a little bit. So on 0, +3, f is concave down because f prime is decreasing. Finally, on 3 to 4 open, f is concave up because f prime is increasing. And then we have inflections of f wherever we have a change in f prime, decrease to increase or increase to decrease. In other words, maxes and mins. So we're going to have inflection points of f at x equals -3, x equals 0, and x equals +3. Once you've done a few of these, you get good at it. It becomes easy. That's all it really is necessary for us to answer all of these questions about the concavity of f based on the graph of f prime. I hope this has been a good, quick, useful introduction to concepts of concavity. Happy mathing.